You've been there. Trying to secure those limited concert tickets, you tap checkout, and the app vanishes. Just a sudden, unceremonious black screen. Writing instructions that a computer can execute in perfect conditions is relatively easy. But if a developer doesn't actively write code to handle the exact moment things go wrong, they aren't truly programming. The first layer of software defense is the Java compiler. It catches simple syntax mistakes, like a missing semicolon, before Bit4 is even allowed to run. These are called compile errors, and they are easily fixed. The real danger lies in the runtime error. This happens when the syntax is perfect, but a chaotic real-world event, like a dropped internet connection, disrupts the system while the application is live. The boundary between a functional application and a catastrophic crash comes down entirely to how the code prepares for these unpredictable moments. When the Java virtual machine encounters an unexpected anomaly it can't resolve, it panics. The normal execution flow instantly stops. In its final moments before shutting down, the system spits out a stack trace. This forensic list tracks every method the program called, down to the exact line of code that triggered the failure. The trigger could be a math operation attempting to divide a number by 0, or a database query asking for the 10th item in an array that only holds 5. If there is no mechanism built into the code to intercept these system panics, a minor environmental hiccup instantly becomes a fatal termination. This chart maps out the entire anatomy of Java software failures. Everything stems from the throwable class at the top, which divides system chaos into two distinct branches. On the right side, we have errors. These are severe, unpredictable environmental fatalities, like a server running entirely out of memory. Developers cannot realistically write code to recover from these. The left side shows exceptions. This is the active battleground where developers can intercept failures and fight back. Exceptions are further split. First are checked exceptions. These are risks verified before the program runs, like trying to read a missing file or a dropped database connection. Java actually forces programmers to write a backup plan for these before the code compiles. Next to those are unchecked exceptions. The compiler doesn't warn you about these because they stem purely from bad programming logic, like a NullPointerException, where the code tries to use an object that hasn't been created yet. Identifying exactly which branch of this tree a failure belongs to is the required first step, before a developer can construct a defense to stop it. That defense is built using a specific coding architecture known as the try-catch-finally block. The try block acts as a containment zone. It holds the risky, real-world application code that might fail, like attempting to read external files or write data. If things go wrong inside that zone, the program throws an exception. Instead of crashing the entire system, the catch block immediately intercepts it, allowing the software to report the error gracefully to the user. Because different operations fail in entirely different ways, developers can stack multiple catch clauses together to handle specific types of exceptions simultaneously. The final piece of the structure is the optional finally block. This acts as the mandatory cleanup crew. It always executes, regardless of whether the try block succeeded perfectly or failed and triggered a catch block. If you open a database connection in the try block, you use the finally block to close it. If you don't guarantee that connection is severed, the system will slowly bleed resources until it triggers a fatal memory leak. This simple three-part sequence is what turns a complete software shutdown into a smoothly managed disruption. Sometimes, the exact block of code where an error occurs is not the right place to handle it. In those cases, developers delegate the responsibility. Using the throw keyword, a developer can programmatically trigger a specific exception on demand, sounding a targeted alarm within the system. They can then attach a throws clause to a method's signature. This legally passes the burden of catching and resolving that exception up the chain of command to whichever part of the program originally asked it to run. But there is a strict limit to this delegation. If you push the exception all the way up the chain to the main method without catching it, the main method will throw it out to the operating system, and the application crashes anyway. Exception handling operates as the invisible safety net of the digital world. While anyone can write code for a perfect environment, But a system's true durability is proven only when it survives the chaotic, unpredictable friction of the real world.